Okay, let's implement the backward together. To calculate gradients, we first need to retrieve the parameters. That is going to be self.params. And we also need to retrieve the cached items, like this. And here, we're first going to calculate the gradient in respect of hypertangent here. How do you calculate the gradient of hypertangent? First, this is the upstream gradient times the gradient in respect of hypertangent. And we haven't talked about this in class. However, when you derive it on your own, you'll easily understand that the derivative of hypertangent is 1 minus x squared, like this. Okay. After then, the derivative of b is going to be just sum of dt along the axis 0. We've done this a lot, right? And the WH is going to be NP dot H pref transpose and dt. In the H pref NP dot dt WH transpose. WX NP dot X transpose dt. dx NP dot dt WX transpose. So these are what we've done a lot in the previous sessions. And we need to store the gradient we've calculated, dwx dwh db. You're going to return dx and dh prep. Okay. However, one of the problems of this RNN is it's not quite easy to use. What I mean by this is when you want to process a sequence of input, what we need to do is first create an RNN instance like this. And let's say our input looks like this. And when we want to deal with this, I would of course need to initialize with the corresponding parameters. What we need to do is something like this. And for each x, we put rnn. After setting h ref at 0, h there is one problem here. This one should return h like this. And current h ref becomes the next h ref like this. And we do kind of things like this. However, this job is somewhat repetitive and we need to do this again and again for using rnns. So from now on, what we're going to do is we're going to make a class called time RNN. What it does is basically the dirty jobs to use RNNs on behalf of us. This one is just a normal computational block. And what we are going to do is receive a sequence of x. So it's not just one vector, however, a sequence of vectors. This one also gives dh, multiple dh, that is s. Okay, how are you going to implement this? First of all, we need to define the parameters. They are going to be wx, wh, and b. Self-breadth are going to be just the same as zeros like x and b zeros like wh, zeros like b. And here we're adding one more parameter, an attribute, class attribute, that is layer. Self h and self dh, none, none. Self stateful, full state. Okay, what does it mean by stateful? Stateful means this time RNN contains, keeps track of the state h. It will be clearer when we implement a forward method. If stateful is false, then when we accept new input, then we are going to initialize h and dh again. However, if stateful is true, then we'll just keep track of h and dh. Okay? There is a typo. Okay, let's implement forward method together. We first need to retrieve the parameters like this. And xs has this shape. So we have n samples, number of batches, and t is the length of the sequence, and d is the dimension of the vectors. dh is going to be the dimension of wx. And we initialize self layers as a empty list. And we're going to keep track of h as well. Each time step, we need to store the state of h because we need this to calculate gradient. And this is going to be the same shape like this. And the data type is float. And here, we're going to use not self-stateful or self-h is not. Then we initialize self-h as b zeros and h. Therefore, if stateful is true, then it means we're going to use self-h from previous input. Okay? And for t in range t, we're going to do some operations, and we're going to return hs. Okay, think about how we can implement this part. And after that, think about how you can implement the backward path as well. Okay, see you in the next video.